Hello everyone, my name is Mitali and I am All India Rank 48 and today I am going to discuss Database Management System PYQs. So let's start with the PYQs. So this is our first question. So the first question is, from the following instance of a relation schema R where the attributes are given A, B, C, we can conclude that. So with the attribute, we have also given a table where A has some values, B has some values and C has some values. Okay. So the four options are given. Let's verify option one by one. Okay. So option A says A functionally determines B and B functionally determines C. Okay. So let's check option by option that which is correct answer. Okay, so what this statement is saying? A functionally determines B. So let's check if this is true for this table. So 1 and 1 is there, 1 and 1 is there, 2 and 3 is there, 2 and 3 is there. So we don't have any problem. Means see, 1 and 1 are there, but they both have same values. They don't have like one don't have different values. Like one is with one and other one is also with one. Problem where we will have problem where one has two values, at that time we will have problem, but here one don't have two value, it only has single value, so we don't have any problem. Similarly we can say this too for 2 also. Okay, 2 also have same value, one value which is 3, so we don't have any problem. So for this table it holds. For this table it holds. Okay, so this is point number 1. Let's go to point number 2, and what we can say, what it is saying, B functionally determines C. Okay, so let's check that B functionally determines C, it holds or not. So C, I was saying, right, in first we for 1 we have only one values which is 1, but C for B, here 1 has two values, here it is 1 and here it is 0. So this is not allowed. It should have only one value, but here for 1 we have two values. So we can say that 1 has two different values. Two different values, 1 and 0. So from this we can say that B determines C does not hold. B determines C does not hold. So I hope this is clear. So option A is wrong. Why? Because here they are saying that B functionally determines C, which is wrong. Okay, so let's see. So option B we will see A functionally determine B and B does not functionally determine C. Okay, so option C, as per to this conclusion, option C is correct. Option B is correct. But I want to tell you something. But let's verify option C. So B does not functionally determine C. This is exactly correct because exactly we have seen this. So we will mark it. D is not correct because for this table A is functionally determining C. So here itself D will get wrong. So we have the solution. We have to conclude between B and C. Okay, so let's go for B. So what we can say about B? Okay, so A function determines B. So see, this is for the particular instance, for the particular table we can determine A function determines B. But in future there may be uh, the values may be add in A and B. So at that point of time we can't say that this relationship will hold. Okay, so we can't say that. So that's why here, as a future perspective, if we will see, then we can't say that if this will be functionally dependent or this A determines B will hold or not. But but what about B and C? This holds. See, if one is wrong, if one is defective, there is no chance if future values add or not add, it will be defective because we have this, we have this case, any future values will add, it may not define that it will be, it will be hold. if it is not holding for some in this instance only, so in future also it will not hold. So this is the conclusion we can make, that the only conclusion we can make, that B does not functionally determine C. That's why C answer is correct and B answer we are not considering, because if they have asked for this particular instance, so no doubt option B is correct. But in future, but they have not asked for this particular instance. What they have asked, um, in general they have asked for. So that's why what we concluded, that in A there may be values added, so this relation will not hold. Okay, and we can't say that in future functionally determines A functionally determines B. But here we can conclude that B does not functionally determine C, because in future the values may add, but for this reason, but for this entries, it will always be not functionally determined. Okay, so this is the solution. That's where our option is C. I hope this question is clear to you all. Let's move to next question. Okay, so next question is the relational schema. We have the relational schema student performance, and here some attributes are given. So the student performance is generally a table, name. Okay, the table name is student performance, and there are four attributes: name, course number, roll number, and grade. Okay, we have four attributes, has the following functional dependencies, and the functional dependencies has also given, which is 1 2 3 4. So four functional dependencies are already given to us. It is given in the question. So what the question is saying, the highest normal form of this relation schema is, you know so let's calculate first of all for this region, for this solution, we have to calculate NF, highest normal form. So for that we should know what is candidate key, we should know what are prime attributes, and we should know what are non-prime attributes, because on this region, on this whole information only, we can say that this is this normal form or in that normal form. Okay, so let's say that name and course number, let's take the attribute closure of this. So we can have name, course number, and with this we can get grade. Okay, and yeah, from roll number we can get, okay, yes, it is completed, I guess. No, roll number is left, so from name, here we can take roll number. So look, from this we have derived all the attributes, so that's why we conclude that name and course number, okay, this is CK. CK means candidate key. Okay, now let's check for roll number and course number. Do they derive all the attributes? So let's check here. Let's check the attribute closure. You know, so roll number and course number. If we take the attribute closure, so we will get roll number, course number. And here they are deriving grade, and with, so name will be derived from roll number itself. So name is also deriving. So in this case also all the attributes are derived, of this, all the attributes are present. So that's why we can say that roll number and course number are also candidate key, So let's check quickly that name can derive all the attributes or not. And if it is deriving, then name is also a candidate key. So name, if we take attribute closure of name, so it will be name, roll number, and from roll number are we going to derive anything? Are we able to derive everything? I guess no. From this we cannot derive anything. So that's why this is not candidate key. Let's check for roll number also. So if we take attribute closure of roll number, so we will get roll number, name, and from roll number name, are we going to derive everything like grade and course number? Can we derive? Clearly we can see from the dependencies we cannot derive them. So that's why roll number is also not candidate key. So we can finally say that our candidate key are name, course number and roll number course. This is our candidate key. So from candidate key we can say that what are prime attributes and what are non-prime attributes. So let's see what are prime attributes. So prime attributes are the one who are part of key. So name is prime attribute, course number is prime attribute, and roll number is also prime attributes. And non-prime attributes are the one who are not part of key. Okay, non-prime attributes. So apart from this, what is left? Like name is covered, roll number, course number is covered, roll number is covered. Now only thing left is grade. So grade is non-prime attribute. Okay, now we all have this information. Now let's check which normal form it comes. So first of all, let's clear this so that you can have better understanding of things. So for that we have to check from start, we have to check. Okay, like from first NF we should check, like, okay. So this is already in first NF. Okay, now let's check for 2NF. If we will take if we will check for 2NF, so this, if we see this dependency, this is already key deriving grade, so we don't have any problem for this. Then second is roll number, you know, roll number is deriving grade, we don't have any problem for this. So for 2NF we have to check that whether it is partial dependency or not. We have to check that, for 2NF we have to check for partial dependencies, and for 1NF we have to check that the values are atomic or not. But for this kind of question it is already atomic values. So in 2NF we have to check that is there partial dependency present. Okay, so let's check. So this is itself a key, so it does not have any partial dependencies, so this is clear. This is also the key, it does not have any partial dependency, so it is clear. Now name has partial dependency, okay, because our candidate key is name and course, and it is the part of key which is name, so it is partial dependency. But in the left side we can say that it is already a prime attribute. If this side has non-prime attribute, then we can say that it does not follow 2NF, but this is prime attribute itself. That's why on the other side this is partial, but it does not matter, so that's why it also follows 2NF. And similarly here also, roll number is partial, but on the right hand side it is prime attribute, so that's why it will work. Okay, that's why it will work for 2NF also. So the relationship is in 1NF, it is in 2NF. Now let's check that the relationship is in 3NF or not. So how we check 3NF? So if LHS is key, for 3NF, LHS should be key or RHS should be prime attribute. These two criteria should happen, and it is or either can work. So here if we will see this side, so it is key, so that's why it is in 3NF. Here also it is key, that's why it is in 3NF. Name is not key, but roll number is prime attribute, that's why it will work. Here roll number is not key, but name is prime attribute, so it will work. So that's why it is also in 3NF. I want to let you know that the property of 3NFs are, LHS should be a key or RHS should be a prime attribute. Okay, and more than this, before checking this condition, you should check that it should be in 2NF first. For 3NF, these are the conditions. Like first, it should be in 2NF, and second, the LHS should be a key or RHS should be a prime attribute. So the two conditions are matched here. That's why it is in 3NF. Now let's check for BCNF. Okay, because an option BCNF is also given. And if it is following BCNF also, then we will check for 4NF. Okay, so what is the property for BCNF? Like the mandatory property for BCNF is LHS should be a key. This is the only thing we have to check in BCNF, that this left hand side should have a key. And if does not have a key, then it is not BCNF. It is very simple. BCNF don't have to do with, if it's prime attribute or non-prime. We will not check. Only the left hand side we will check. If it is key, then it is BCNF. Otherwise, it is not. So let's check one by one. For this dependency, it is a key. That's why this comes in BCNF. This is also key. That's why this also comes in BCNF. But is name a key? No, it's not. So that's why this is not BCNF. Our roll number key is roll number key. It is also not key. So that's why this is also not BCNF. So for BCNF, all the dependencies should be under BCNF. Only two dependencies are BCNF and others are not. This will not work. This we can't say that the whole functional dependencies are BCNF. So that's why the highest normal form we can say is 3NF. Because BCNF failed. BCNF. So let me write the reason why BCNF failed. Okay. So BCNF failed because in third and fourth functional dependencies uh, on LHS we don't have key. That's why they are not in BCNF. So that's why they are not in BCNF. So the highest normal form is in 3NF. I hope this question is clear to you all. Okay, so let's move to next question. So here the question says, which normal form is considered adequate for normal relational database design? Which is adequate. So, so the reasoning we can give here is 3NF. The answer is 3NF. 3NF is considered as adequate for normal relational database design. Okay, because we have the reasoning, because we always have 3NF decomposition, which is dependency preserving and lossless. Okay, so it is not in all possible or in any higher forms. That's why it is 3NF. Okay, so and also we can say that 3NF will be adequate for relational database design, since 3NF tables are free of insertion, update and deletion anomalies. Okay, so that's why we have chosen 3NF. So let me write the reasoning for this. 3NF will be adequate for normal relational database design, since 3NF tables are free of insertion, update, and deletion anomalies. So that's why for the design purpose we are choosing 3NF. Okay, so 3NF also ensures that both lossless and dependency preserving. But why not BCNF? Because BCNF, dependency preserving, is not always, although it is more strict than 3NF. Okay, you can have questions like why not BCNF? So let me write the reasoning of BCNF. BCNF, dependency preserving, is not always possible, although it is more strict than 3NF. It is more strict than 3NF. So that's why we chose 3NF or BCNF. Okay, so I can also say that both the reason, we are choosing a 3NF or BCNF because we normally choose to retain dependency preservation. Okay, and a highly penalty in the system performance is to be paid or the risk integration of the data in our database. So both the reason describe the nature of preference, or security and the data over the redundancy, which is satisfied by 3NF. As I already mentioned that 3NF also is free in insertion, update and deletion anomalies, and also it gives more preference to security and data redundancy. Okay, and although BCNF also satisfies this all property, but the only thing is that dependency preserving is always not possible in BCNF. BCNF do have these properties, but dependency preserving is not always. That's why we have chosen 3NF over BCNF. This is the only reasoning. In short, we can say that because the dependency preserving is not always possible, you know, and it is also strict also, so that's why we have chosen 3NF over BCNF. And here let me write the other reasoning also for 3NF. So because we can always have a 3NF, and if it is 3NF then of course it is 2NF, and 1NF, and here the BCNF is not possible, so we can't expect 4NF or 5NF in relational database design. So that's why 4NF and 5NF is also not possible because BCNF is only not satisfying, so that's why we can't say. But if it is 3NF then 2NF will also do and 1NF will also do. But 2NF here, because in 2NF we can't guarantee, there is no thing like dependency preserving and everything, lossless dependencies. We can't talk at that level these things. So that's why 3NF is only suitable answer. So because we can always have a 3NF, decomposition, which is dependency preserving and lossless, so not possible for any higher form. So these are two reasonings for 3NF, why it should be 3NF, and this is one reasoning why it should not be in BCNF. And if it is BCNF, so these options are already crossed. 2NF, so the higher form we want, so that's why this is also not correct. So the correct option is 3NF, which is option D. Let's move to the next question. So here the question says that consider the schema R, and the attributes are given as S, T, U, V, and the dependencies are given S determines T, T determines U, U determines V, and V determines S. Let R equals to R1 and R2 decomposition. So R is decomposed into R1 and R2. Means we have some dependencies here, and R2 will have some dependencies here. But the thing is that decomposition, this, if we will take intersection of this two, so it will be equals to null. It will be equals to phi. We don't have anything common here. So the decomposition is, in. Okay, so let's check via by dependencies. Okay, so S determines T, T determines U, U determines V, V determines S. So for this, let's find candidate key first. Okay, so if we take clean closure of S, so it is S, T, U, V, and again S. So S, T, U, V. This is determining everything. Okay, this is determining everything. So that's why S is candidate key. S is candidate key. Now let's check for T. So T, U, V, and V is determining S. So S, T, U, V. So T is also CK because all the attributes are present. So if all the attributes are present in attribute closure, then we have to consider it as candidate key. CK is candidate key. CK is candidate key. Okay, so this is completed, this is completed. Now let's check for U. So V is determining S and S is determining T. So yes, U is also CK. Okay, and V. If we take a clean closure of V, so it is V, S, and S is determining T and T is determining U. Okay, so V is also CK. So here all are CKs, okay. So the whole relationship is in BCNF. Because why they are in BCNF? Because all the left hand sides LHS are key. All the left hand side LHS are key. So that's why the whole relationship is in BCNF. So that's why option D is correct. If it is in BCNF, so definitely it will be in 2NF and 3NF. So let me write what is BCNF. So BCNF, if we have to check if it is BCNF or not, so LHS should always be a key. LHS should always be a key. And here S is key, T is key, U is key, and V is key. So the whole relationship is in BCNF. And if it is BCNF, then most surely means 100% it is in 2NF and 3NF. Okay, so with this method, we can conclude this. But what if we don't have to calculate the CKs and we just have to, conclude from this line? We just have to check whether from this line if it is 2NF or 3NF or not. Okay, so I also have the reasoning for this. So this is method 1. By candidate key also we can check. Now let's see the other things. Okay, so R, so in question we have given R intersection R2 is equals to phi. Okay, is equals to phi. So what this says, that this makes the decomposition lossless join, as all attributes are key. If it is phi, as we have seen all attributes are key, so that's why this decomposition is lossless join. Okay, and R intersection R2 will be key of the decomposed relation. Lossless condition says the common attribute must be what is lossless? What is the condition of lossless? That whatever common will be here, it should be key. It should be key at least of the decomposed relation, means it should be a key of at least R1 or R2. This is what lossless means. Now, even the original relation R is in 3NF, even in BCNF, as we have seen, the relationship itself is in BCNF because all are the prime attributes. Because all are keys, so all are prime attributes. That's why here we can say that the decomposition is also in 3NF because the whole relationship is in BCNF. Okay, so let's write the condition for lossless join. Lossless join. First write what are the condition of lossless join. The common attribute must be a key in at least one of the decomposed relation. So this is lossless join. Okay, and now R1 intersection R2 is 5. So this makes the decomposition lossless join. This makes the relation lossless join as all attribute are keys. As all attributes are key. Okay, and for the lossless join, the common it should be a key. So this is the condition, and if all are the keys, then definitely it is in BCNF, and if it is in BCNF, so it is already in 2NF and 3NF. So that's why option D is correct. I hope you understand this question. Let's move to next question. Okay, so what the question says, given the following relation instance and the instance is given x, y, z, and we have some values. So which of the following functional dependencies are satisfied by the instance? So we have to check, So the first, so let's check one by one. So first check option A. So what we have to check in option A, x, y determines z. So what are the values of xy? Let's write down here and let's check for z. So xy value is 1, 4. What it derives? 2. Then 1, 5. It derives 3. Then 1, 6. It also derives 3. And 3, 2. It derives 2. So if LHS is always unique, so this dependency will always hold. So if it is unique, so the dependencies will always hold, and 1, 4 is unique, 1, 5 is unique, 1, 6 is unique, and 3, 2 is unique. Why we are saying unique? Because 1, 4 here, 1, 4 is not present anywhere. 1, 5 is also not present anywhere. 1, 6 is 1. That's why it is unique. So if LHS is unique, so definitely RHS we have any value, we don't care. Here any value we can have. So it does not matter and it will always hold. So if this is the case, it will always hold. It will always hold. So okay, I'm not marking the option because we haven't made the conclusion. Okay, now let's check for z deriving y. Z deriving y. So let's write it one by one. So y values are 2, 3, 3, 2. Y values are 4, 5, 6, 2. So can you see that RHS side is not unique because we have 3 threes. We have 2 threes. That's why it is not unique. So we have to check one by one. So this will not match. So we have to check manually. Like 2 is 4. This is okay. But for 3, we have 2 values. We have 2 values. So LHS should not have more than 2 values. So LHS should not, so LHS for a particular number should not have two values. LHS for a particular number should not have two values. Should not have two values. And here we have two values for 3, which is 5 and 6. So here itself it does not hold. So it does not hold. So we can say that this is A is wrong. Let's check for B now. Similarly, we will check for all the options B, C and D. So YZ is determining X. So YZ values are 4, 2, 5, 3, 6, 3, 2, 2. And it is determining 1, 1, 1 and 3. So what the first thing we have to check, that is our LHS site unique. So 4, 2, 5, 3, 6, 3, 2, 2. All are unique values. And we don't have to check for RHS. RHS may have duplicates value, may have unique value, we don't care. It will have any values, we don't care. But LHS should be unique. So, and it is unique. Okay. So that's why that's why YZ is holding this. So it holds. Okay. Now let's check for Y determining Z. Let's check for this. So let's write the values for Y. 4, 5, 6, 2, and the values of Z are 2, 3, 3, 2. So here also these are all unique values. These are all unique values. 4, 5, 6, 2 are all unique values. So we can have in RHS any value. So this will also hold. This will also hold. So that's our option is, correct option is B. But we have found the correct option, but still we will go for all the options. Okay. Let's check for C and D. So you will have better understanding. Okay, so y, z and x. So let's write the value of y, z. It is 4, 2, 5, 3, 6, 3, 2, 2, and here 1, 1, 1, 3. So the values are all unique. So that's why we don't have to check the RHS side. So that's why it holds. Why it holds? Because RHS value are all unique. It holds. Okay. Now let's check for x and z. So 1, 1, 1, 3, and z values are 2, 3, 3, 2. So for 1 we have 2 also, for 1 we have 3 also, and for 1 we have 3 also. So 1 has LHS, 1 has 2 values, 2 and 3. So this is clearly violating the law. Of dependencies, functional dependencies, this is the violation of law. Like LHS value, any of the value cannot have more than one value. It should only have one value. So that's why this is wrong. So option C is gone. Let's check for option D. Okay, so xz determines y. So xz, so 1 2 1 3 1 3 3 2 4 5 6 2. So here also 1 3 has two values, which is incorrect, which is violating the law of functional dependencies. That's why here itself we can't say that D is not correct. And here and is there, this also should be correct, this also should be correct, so we can take the whole answer, but here itself this is false. So everything is false. So that's why we will not check for y and x. For the better understanding, let's check, but here itself we can mark that option D is incorrect. But for our understanding, we will also verify this option. 4, 5, 6, 2, 2, 3, 3, 2. So this is all unique value. This is all unique value and it is holding also, but here itself this is not holding. So that's why if it is true or false, it does not matter. That's why our option D is incorrect. So the correct answer is B. I hope this question is clear to you. Let's move to the next question. Okay, so this is the question. Consider the following functional dependencies in database, and here the functional dependencies are given. The relation roll number, name, date of birth and age is. So this is the only relation we have given. These are the attributes we have given, and as per the attributes we will select the functional dependencies from here, and then we will check which normal form it belongs to. Okay, we don't have because the attributes are already given to us, so from that attributes only we have to check. So let's write the attribute here for better understanding. Attributes are roll number, name, date of birth and age. Okay, this is given. Now what the attributes belong to here? Date of birth and age are there. Date of birth and age. Okay, so we can take this. Name and roll number is there. Yes, we can take this dependencies also. Course number, course name is there. Here is there any course number, course name? So we can't take this because it will not lie. Here roll number, course number and grade is there in any of these attributes. So no, we cannot take these dependencies also. Age is there, but eligibility is there in this attribute. No, it is not there. So that's why we will not consider this. Roll number and name is there. Yes, we will consider this. Course number and instructor is there in these attributes. No, we will not take this because the attributes are already given. And for this attribute only we have to check the dependencies. So what dependencies we have? Date of birth, age, name derives roll number, and roll number is deriving name. So we only have these three dependencies. Okay, 1, 2, 3. We only have these dependencies. Okay, so for dependencies checking, so which normal form it belongs to. So for that we have to calculate CK, which is candidate key. So let's calculate CK. So date of birth, from date of birth we can derive, if we will take the attribute closure, so date of birth we can derive, sorry, date of birth we can derive itself, age we can derive. From age can we derive anything? No. So date of birth is not candidate key, gone. Let's check for name. Let's check for name. So name we can derive, roll number we can derive, and from roll number can we derive date of birth and age? So no, name is also not candidate key. Now let's check for roll number. So roll number is there, name we can derive, but can we derive date of birth and age from these dependencies? No, we can't derive. So that's why roll number is also not candidate key. Now let's check for the combination, like roll name, roll date of birth, roll age, like this combination we should verify, and we should check for the candidate key. Okay, so roll number, name. Let's check for this attribute closure. So of course it will derive roll number and name. So can it derive anything other than this? No. So that's why this is also not key. Let's check for roll number and date of birth. So roll number and date of birth. So if we do closure, so roll number we can derive, date of birth is there, and from roll number name is deriving, and from date of birth age is deriving. So yes, we have all the attributes present here. So that's why we can say that roll number and DOB, date of birth, is CK. Okay, let's check other CKs also. Let's make the combination and let's check for them also. Okay, so roll number, name we checked, we didn't get anything. Roll number, date of birth we checked, so we got CK. Now roll number, age we will check. Roll number, age, if we check for this, then it is roll number, name, and from age can we derive anything? No, we can't derive anything. Okay, so that's why this is also not CK. So what the combination is left then? Name and roll number we have already seen. Name and date of birth, let's check. Name and DOB, let's check for this. So from name we can derive roll number, and from DOB we can derive age. So that's why this is also CK. So name and DOB is CK. Name and DOB is CK. Okay, and what combination is left? Name and age. So from name we can derive roll number, and age we can't derive anything. So DOB will be not there in attribute. So that's why we can't say that that name and age is CK. And date of birth and roll number, this is already there. Date of birth and name is already there. Date of birth and age if we take, so we can't derive anything, because from date of birth is already derived, and from age is there. So name and roll number will be left, and we can't say it is as CK. Okay, so this is the CK. Two CKs we find. First is roll number, date of birth, and second is name and date of birth. So without doing all this process, I have a shortcut for this, of finding CK. Let me explain with you. So for that we have to make a table, like this kind of column, horizontal table. Let's make here. Let's write DOB. Then we will write all the attributes, we will write one by one. For this, all the attributes we will write. So first is roll number, second is name, third is DOB, and age. So what is deriving, we will make it as arrow. So like date of birth is deriving age, so date of birth is deriving age, so in age we will have arrow. Name is deriving roll number, name is deriving roll number, so here we will have arrow. And roll number is deriving name, so here we will have arrow. Okay, we will have arrow. So whatever the thing, whatever the column we don't have arrow, we will take it as key. So here arrow is there, so we can't take this. Here arrow is there, so we can't take this. Here we don't have arrow, so BOD, and here we have arrow, so we can't take this. After taking this, let's derive the attribute. DOB, let's derive the attribute. So from DOB we will only get age, and we still don't have name and roll number. So this is not candidate key. But if it is not deriving anything, then from this only we have to make the combinations, so it will derive things. See, in this also DOB is common, and from that we have taken we have add other attribute also, and then with this it is forming CK, but DOB is mandatory in this. So if the attributes are not forming, so make the combination from this only, DOB only. So we made the combination of roll number and checked, so it is CK. We make the combination with name and it also forms the CK. DOB combination we can't make, then DOB age combination we made, but it is not forming CK. So that's how you will check. Okay, that's how you will check. So now let's come to the question. So roll number, DOB. So from CK we can also say that what are prime attributes. So prime attribute is roll number, DOB and name, and non-prime attribute are, what is left, it is age only, I guess it is left. Yes, age is only left. So let's check here, date of birth, so see, this is violating 2NF because date of birth here is partial dependency, because roll number and date of birth is CK and part of key is date of birth, and which is partial dependencies. And also if we checked right hand side, so it is non-prime attribute, so that is why it violates the law of 2NF, and it is not in 2NF. It is in 1NF but not in 2NF. Okay, if age is prime attribute, so we can consider this, but age is non-prime attribute, so we can't consider it. And also name here is partial dependencies, but roll number is prime attribute, so we can consider this in 2NF. We can also consider this also in 2NF because roll number is partial dependencies but name is prime attributes. But here one is not following, so the whole relation is not in 2NF. If one only we will get that it is not in 2NF, so whole relation, other dependencies are also in 2NF, so we will not care about this because one itself we find effective for 2NF. So that's why what the option will say, in second normal form but not in third normal form. This is clearly wrong because it is itself not in second normal form. So how it can be in third normal form? In third normal form, but it is not in BCNF. It is not in 2 normal form itself, so it can't be in 3NF. Okay, in BCNF, this is clearly wrong because it is also not in BCNF. So what the option correct is? D. So in place of D, we can write it is in 1NF but not in 2NF. It is in 1NF but not in 2NF. So this is the correct answer for this. Okay. I hope this question is clear to you all. Thank you. Consider a relation schema R and the attributes are given as A, B, C, D, E, H, on which of the following functional dependencies hold, and the functional dependencies are given. Following functional dependencies hold. What are the candidate key R of R? This relation, what is the candidate key? Okay, so what are the dependencies given? Let's write down here. A is determining B, BC is determining D, E is determining C, and D is determining A. Okay, so these are the functional dependencies given to us. So we have to calculate candidate key. So by normal approach we will go first and then I'll also tell you the short trick of this. So let's check for A. So A itself is determining A, B, and B is, can we derive anything from here? No, I guess. So A is not candidate key. Cross. Let's check for BC. So B, C, and here we can determine A, derive A. D here. From BC we can derive D, and from D we can derive A. Okay, and can we derive anything else? C and E and C are left, so that's why this is also not CK. Let's check for E. So E also here. So E, C, and can we derive anything from C and E? No, we can't. So that's why this is also not CK. And from D, if we will see, so D, A, and from A we can derive B. but we can't derive anything else from here. So that's why this is also not CK. So what is CK? Everything we checked from this. So for CK, we have to make the combinations now. Okay. So my short trick will give you like idea which combinations to make. Okay. So let's discuss the short trick. So we have to make a horizontal this. We have to add the attributes A, B, C, D, E and H. So as per to given, we will draw it like A is deriving B, BC is deriving D, E is deriving C and D is deriving A. So after that, what is the step? Which attribute don't have arrow? We have to consider that. So A has attribute, A has arrow, we will not consider this. B has arrow, we will not consider this. C has arrow, we will not consider this. D has arrow, we will not consider this. E and H don't have arrow. E and H don't have arrow. So let's check the attribute closure of this. E, H. From E we can derive C, and from C can we derive anything? So no. So you will say how this is key? This is not key, but this is part of key. So with this combination, if we make combination with A, B, C, D, we can get a key. There are high chances to get a key. So from option itself, we can say that this is mandatory to present. E, H should be mandatory to present. So here in option C, E is present but not H is not present. So that's why option A is wrong. In option B, E and H should be present with the combination. So this is also not correct option. In C, E and H is present, E and H is present, but here C and H is present. We don't want. What is mandatory? E and H should be present. So that's why this is also not correct. But option D, E and H is present, E and H is present, E and H is present. So that's why D is correct. So that's how we can check quickly. But let's check like now E and H should be mandatory. Okay, and now we will form the combination with this. So let's form the combination with A first and let's check them. A, E, H. So A will derive A will derive B, and E is there. So E will derive C, okay, and BC will derive D, and D will derive already derived A, and H we have. So see, with this combination, we have all the attributes. All the attributes are there. Okay, so that's why A, E, H is the key we formed. Now similarly, let's make it as B. Let's make the combination with B. So B, E, H. Okay, so from B can we derive anything? No. From E we can derive, C we can derive. And from BC we can derive D. And from D we can derive A. And can we derive H? Yes, H is also derived. So here we can check all the attributes are present. So that's why BEH we can also take. After that, EH we can make combination with C. Let's check CEH. If we make the combination, so CEH. So can we derive anything here? From C can we derive anything? No. From E we already derive C which is present, and from H we can't derive anything. So that's why this combination fails. Okay. Then let's make combination with DEH. So DEH. So from D what can we derive? A. And A we will derive B, and E derives C, and BC we will derive A, and H is already present. So that's why DEH also is a key, and then EH is only present. So that's why. So that's how we will get an idea. That's how we will get an idea that what is mandatory. If it is, see, in some cases this combination will only derive everything, so we don't have to check. We don't have to add other things. But if it is not deriving anything, so we can make the conclusion that this is mandatory, but for deriving all the attributes we have to make combination with other attributes one by one, and then we have to check. But the mandatory thing is this. So from this table, so from this shortcut we can get that idea. Okay, so I hope this question is clear to you all. Let's move to next question. So what is next question? The following functional dependencies are given. This is the dependencies. Which of the following options are false? Okay, so attribute closures are taken and we have to check one by one. So which attribute closure is wrong? Okay, so so let's write the dependencies first. AB is CD, AF is D, DE is F, G, C is G, F is E, G is A. So let's take the attribute closure of C, F. So definitely C and F will be present, and after that from C we can derive G. So G is also there. From F we can derive A. Sorry, E is also there. From G we can derive A. So A is also there. And what else we can derive? Yeah, this much only we can derive. Can we derive D? Let's check. D and E. Okay, A and B is also not present. A and F is there. So from A and F we can derive D. Yes. Okay, D and E. Is there anything present? We have derived F. F is already there. So I guess B is left and we can't derive B from anyone. Okay, so we can't derive that. So let's check. Yes, A is there, C is there, D is there, E is there, F is there, and G is there. So this is the right attribute closure. But what we want? False. Okay, so let's check for BG. Let's check for BG now. So we want false, so that's why we can't take. So BG, if we take attribute closure, so it will be B, G. From G we can derive A. From AB we can derive CD. And what we can derive? DE, can we derive anything from DE? E is not present. So from B can we derive? No. From G we can derive. We derived A. From A can we derive? We already derived CD. And C, G is there. From D we can derive? No. So this much only we can derive. So let's check here. Yes, A is there, B is there, C is there, D is there, and G is there. So this is also correct. Correct attribute closure. Now let's check for AF. Let's check for AF. So A, F, and from F, from F we can derive AE, and other else, can we derive anything from A? AF we can derive D. Okay. DE we can derive F. It is already there. Can we derive anything else? A, F, it is E. F is E and D, and from DE we have already derived. Okay, so we can't derive anything, but only this much we can derive. So let's check A. Okay, we haven't derived C, but here C is present. So this attribute closure is absolutely wrong. So this is our correct answer. Let's check for AB. So A, B, C, D, C, D, C, G, G. Okay, so yeah, this much only we can derive. So A, B, C, D, and G. Okay, so this is also correct. So our correct option is C because it is false. Correct option is C because it is false. C is correct because only that was false. So I hope these PYQs are clear to you all. Thank you.